Back in 2011, I was up about 11 o'clock at night and my house started shaking with like a real earthquake. And I live in Stillwater, Oklahoma. We're not supposed to have such things. And so I was trying to decide if I should wake my son up and get him out of the house. But I formally thought, I don't give Oklahoma enough tectonic credit to worry. But it lasted about a minute, and the house was full shaking. But I was trying to decide if it was going to get worse because I hadn't done full shaking earthquakes. I hadn't lived in such interesting places as Stillwater, Oklahoma. It ended up that I got into this weird role that we're going to talk about here for the next two talks. And I taught environmental geology ever since I was a graduate student. And one of the main things I teach, I do two things when teaching environmental geology. One is I try not to be sexist. And so when I have to kill a little kid because they did something environmentally, I used to just kill Billy. And now I kill Billy and Sally so that I make sure that I am uniform. Title IX. Because the students want to know if somebody would die, and it was sort of very dry and dark to talk about how people would perish in various environmental ways. So I just started killing off Billy because it made it a lot easier. And sometimes 50,000 Billies or 100,000 Billies at a shot. But the other thing I taught in environmental geology was that it's the science of dealing with geology relative to humans. And one of the things I always brought up is that scientists don't communicate very well with humans. We tend to communicate well with each other. When it comes to talking to those other people, you know, it's like the Housewives of Beverly Hills people and those sort of folks. That's not usually science, so we don't usually do well with that. So I ended up having to talk to the public, and I had to go outdoors and things. And I'll talk to you about how the public reacted to that and how other scientists reacted to that. And I basically tested a model based on teaching environmental geology for 20 years of how you would deal with an environmental problem scientifically in a way that would communicate it to those humans. And I learned a lot doing that, so we'll talk about some of those lessons. So first we'll talk about the hydrogeology of induced seismicity. As a science, it's quite interesting because it's commonly, in the situation I'm in, it's generated by wells. But the seismic folks think that they own this problem. It's like, well, how many classes in hydrogeology have you had? None. So why are you the expert and I'm not? Well, have you had seismology? Yeah. Well, are you a registered geophysicist? Yeah. I'm also a registered well driller. I'm a PADI dive master. I've been under the aquifer. So why are you guys in charge? Well, because it causes seismicity. Well, I'm their mechanism to cause it. So it's interesting in terms of doing hydrogeology induced seismicity that it doesn't belong to hydrogeologists, typically. I actually got grant funding rejected because, well, why does the pressure of this system matter? Because you guys don't understand the problem you're working with. Now, this talk actually has its own legal disclaimer. I got to learn that we have a university legal department. They defended me against 3 subpoenas. That was fun. And what it says is that I work at the school, I don't speak for the school. So I'm a professor at Oklahoma State. I am not speaking for Oklahoma State. I've done things relative to seismic activity in our area up in Oklahoma. We hope that will further the conversation. Just don't blame us. We welcome your thoughts and views on the issue. Not a lot of folks talking about cows or wheat have these disclaimers generated, but I got one of these. Largely because people kept calling and asking to have my head on a platter in various sorts of ways. And that was part of this model of what I was trying to accomplish, and we'll talk about that. But I have my own legal disclaimer for these talks. So we'll talk about the context of Oklahoma. We'll talk about its induced seismicity. We'll talk about class 2 disposal wells. We'll go through some induced seismicity science. We'll talk about hazard mapping of this. We'll talk about going into the future. But all along the way, I'm going to slide in commentary about how the slides relate to talking to the public, not just what the topic is on the slide. So I had to tell them why I'm there. And essentially, for oil and gas problems, we can't solve them anymore as it's a technical issue and let's get some data and let's sort out something logical based on data. We must scream at each other that we're all going to die or you have no risk whatsoever, right? And those are the two realities of the teams playing. And joining one of the teams, I don't think is a role scientists want to do. I don't think we're very good at it. We spend all our days analyzing data and then trying to fight about the data on a neutral basis and try to figure out what the data's saying, try to get rid of our instincts. And joining a team to fight for it, we're not good at that. So in terms of marketing our concept or marketing our solutions and all those sorts of stuff, we have no training. And so putting us on one of the teams is like recruiting the person that doesn't even know what a bat is on a baseball team. We're not good at advocating a side. So saying, well, we need a scientist to advocate and fix this problem, I don't think they should be on a team. I think they should be in the middle. And so I think about them as a referee. And so I tell them I'm there to provide the technical reality of what the problem is so that you can make decisions and your teams can go fight it out and do what they're doing, but I'll just play referee and tell you things that are the science supports, it doesn't support, where the uncertainty lies. Now, in scientific referees, there's not one for neutral scientific communicator. Okay, so there's a Dr. Oz for medical, right? So if you watch TV, you can see medical stuff discussed. And Dr. Nancy Snyderman, you can name your different TV doctors, and they'll come on and they'll say, there's a heart pill that just came out. It's got these benefits, these risks, and I would suggest using it if you have this heart problem. This is what came out. This is what the science is saying. Now, not all of those doctors are cardiologists, but they'll also tell you if a new foot thing came out or a new... We don't have that for geology. It's not somebody, you guys don't know the TV geologist. It doesn't exist. So if you have a, hey, what's Flint's water supply problem? Hey, what about this tsunami? What about, is this global warming? We don't have somebody on TV telling you those answers in a neutral sort of, here's the information way. And I found out that the meteorologists feel like they cover that. They feel like they're that role. And I'm like, have you had a geology class? No, but I feel it's Earth. It's the Earth. We could talk about that. Like, no, you can't. Bodies are on the Earth, and I don't think I could talk about a heart. So, but so there's no Dr. Oz for rocks. The other one is that in the energy industry, we don't have an NTSB. Okay, so if we blow up a rig, have a nice spill into the Gulf, if you did that, that's the energy industry equivalent of a plane crash, right? So the airline industry, they have an American labeled plane with a Boeing plane and it crashes. American didn't want that. Boeing didn't want that. But neither one of them sends out their CEO to talk about it. The NTSB shows up, says we're going to figure out what happens. We're going to collect the data. We're the neutral agency to do that. And we're going to tell you what happened. Are you going to tell us if they're bad or good? Nope. I'm going to tell you what happened. You can decide whether they're bad or good, have a lawsuit, this or that. Energy industry doesn't have that. So they go, hey, Acme Oil, you had a rig blow up. Did you guys cause that? Now, they've got a legal context they're working in. They're not going to go, yes, we definitely screwed up, or no, we didn't screw up. They've got a legal context. They got things they can say. And I talked to lawyers about this situation. I didn't just talk to scientists. What can we say? And we went for like 3 hours talking with lawyers and me, trying to figure out what they could say as an industry in their legal context to talk about the problem. And we both got to, you guys can't say anything. So what gets out there then is people that feel like it's okay to say something. So they ask somebody who's okay talking about it, who has no background whatsoever. And that gets to be a problem because we had earthquakes in Oklahoma are caused by it rained and filled up the reservoirs. It caused by the drought because the reservoirs are empty. It caused because it rained after the drought. We had all sorts of ways to make earthquakes, none of which had any data behind them, but they had somebody that would talk on TV. Now, that last part is that if you lose people's trust, you don't just say, hey, I've got a nice commercial on TV and get their trust back. People still are freaked out about nukes and nuclear energy plants and those sorts of things. And this is where the study was done, and people still get freaked out by nuclear power, right, because it's got radiation. Well, fracking, you guys know the origin of the word fracking? It's from hydraulic fracturing is the technical side, but fracking was the second iteration of Battlestar Galactica, and for the F word, they said frack. And so it got applied, and so for many moons, I dealt with the oil industry folks going, they're calling it fracking. I'm like, yep, and you're not going to get them to change that word. But it's derogatory. Certainly is. You should make them change that. They're not referring to the proper part of the system. That's true, but they're not technical and they like the word. So get over yourself and you're going to have to work with the problem some other way. So on both sides, there's things that are happening that you can't fix or change, even though on a technical basis you're like, that's not technically correct. True, it's also not nice to say the F word about your technology either, but that's what they're doing. So I would introduce myself, I built a seismograph as an undergrad because our geologists couldn't pass calculus. And they thought if they came and poached the physicists to come hang out, that their students may pass calculus by osmosis or something. And they didn't have a seismograph, so they asked me to build one. And the only thing I realized is that tequila triathlon t-shirts, you know, in the modern day, in recent events, I'm like, wow, indicating drinking is a good idea in college. Maybe not the t-shirt to wear, but that's the only thing I had on. So there, you know, I did one of those, and I ended up going into geology because the field trips were way better. Physics field trips really suck. So I got the BA in physics and these sort of degrees, so I can talk a little bit about earthquakes or physics. Professor in a geology department, chief technology officer of a commercial firm, and I'm a registered professional geophysicist in California. I was an associate editor for groundwater. I chaired the hydrogeology division, so I can get a hydrogeology checkbox. I was part of the Arbuckle Simpson technical peer review team, so I know something about the Arbuckle Group. I teach a class called Integrated Petroleum Water Resources Management. I've now changed that just to Petroleum Water Management. And I'm on the Governor's Coordinating Council on Seismic Activity. So I'm not a geophysicist who does seismic, but I talk about it on TV. So I had to give him a context that I'm reasonable that this guy could talk about this. Here's one that pissed people off. I put legal terms next to scientific terms, and the lawyers got mad and the scientists got mad. We don't do the same thing. Sure you do, you deal with uncertainty. So a lawyer calls a probable cause, scientifically we call that maybe. Preponderance of the evidence, that's about where liability kicks in, we call 51 percentile. Clear and convincing is about 90 to 95%. And these are both, we've scientifically proven something, right? And then you got 98 to 99 for beyond a reasonable doubt. Beyond a shadow of a doubt, I don't know if science has that, right? But legally they believe they might, right? So putting those together made people angry on both sides of the disciplines, both the legal and the scientific disciplines, because I'm talking about them like they're one thing. And I'm like, well, you need to understand how much uncertainty you have. Yes, you do. But don't use those other guys' terms. It's like you're trying to say you're a lawyer. No, I'm pretty clear I was a scientist. But it was much trickier than I expected to make a graph like this. So why is Oklahoma interesting? Largest change in seismicity in the history of the world. Yay us, we won. We're also managing one of the world's largest industrial waste disposal facilities as cheaply as possible. We're injecting 2 billion barrels of water into the subsurface. Where does it go? The Arbuckle Group. What are the boundary conditions on that? I have no idea. What happens to the fluid? It goes away. That's a problem. So we can do this visually, and it'd be another way to show you the problem. This little map shows you we're a larger hazard than California in 2016. She was there. And it worked earlier today. I did test this. There we go. So this is Oklahoma seismicity with dots. If noise comes on, it's got noise, but she's not there, so it may not have noise. There you go, you can hear it. So that's our background seismicity, location and number. And we're going by year at the bottom, 2004 to 2016. This is when people started noticing maybe it's a little bit out of whack. But we were fighting about it still at this time. What do you think is causing that? I think it's natural. Okay. Seriously, they were debating whether it's natural. At this point, they started believing me. Maybe it's not natural. My house is right there. You want to visit sometime. That circle. So even while it was pretty far from background, people are going, I think it's natural. Why? Because not natural is not good. Let's maybe close all of them. Let's see what happens here. There we go. So we ended up with this hazard, and I got a call from the USGS, and they said, we've taken all the induced stuff off the map. I said, yeah, but we didn't take the hazard off. They're like, well, but they're not natural earthquakes. Well, the shaking's pretty real. Yeah, well, we don't know how to map that. Like, well, you should tell us that we have a risk. Yeah, we're not sure how, because it could change. I'm like, well, then tell me the risk and tell me what it's going to change like, or tell me if it did change. And we had to have some relatively long discussions that I would tell them what the public wanted to know. And then they would start talking about these algorithms where they would do these decision trees. And I had this one conversation that was quite fun, and I said, I need the map to say this. And then one guy goes, I don't know if we can do that. And the other guy said, sure. We go into the algorithm, and he starts listing off all these places they're going to switch the tabs of how the risk calculation is done. I'm like, yeah, do that. So deciding how to do these maps, they wanted to communicate the risk, but seismic folks are actually fairly scared of communicating risk because they might tell you that it's bad. And they said, well, if we show them that would just tell them it's terrible. I'm like, I live here, it's not great. So coming up with a map that they felt was appropriate and useful and would tell you something was a lot of struggle. So one of the things I did when I talked to the legislature, and I had to work out, my expectation of the legislature was that I'd be yanked off the stage in under 5 minutes, because I was going to point out the mechanism that is most likely to be causing the induced seismicity. And to that point, the state had said, we're getting more seismically active. Do you know what's causing that? We're going to measure that. And I was going, I know what's making that. Because it's already in the peer-reviewed literature. I wasn't making it up from data. I was taking the peer-reviewed literature. I was reading to the state of Oklahoma. And I was very careful that I didn't read anything that wasn't already published. I didn't make up any of my own graphs. I didn't make up anything. And the reason I did that was I gave a trial talk at OSU, and there was people giving talks saying, it's all natural, you're fine, don't worry about it. And so I gave a talk explaining the science of induced seismicity, and I had a good curmudgeon that was watching it. I wanted his feedback. And afterwards he says, well, you're just like the other guy. I said, all my stuff's peer-reviewed. He says, well, how do you know? Good point. So everything got labeled. Here's the reference. Here's where it's from. I'm blaming these people for these numbers. As the referee, I'm not part of the game, so I didn't use anything that I wrote. I didn't use any graph I made. I made better color out of the graphs because a lot of the publications were ugly. I'd take the graph and make it pretty, but that's as far as I would take it. So everything's peer-reviewed and labeled highly because it needed to be. But I also put it into a context. So in terms of different sites that have had induced seismicity, I pointed out that here's induced seismicity rates for classical cases here back from the 70s and then up in 2012. Here's our injection rate. I said, the interesting part about this is not writing a paper where you created an earthquake with an injection rate at this size. The interesting paper would say that you injected at this rate and you didn't make an earthquake. So that's the more interesting thing. I said, it's not that we made one, it's that how did you not make one would be more interesting scientifically. And I gave a talk and a guy said, you can't inject at that rate. Here's the thing when naming your wells. If you haven't named a well yet, don't name them after porn stars, because that's what ours were named after, for the really big ones. So I also never will label one of the wells in any of this talk because all the big ones have really embarrassing names to have to talk about in public. I feel sorry for the lawyers in the trials on these things because they're going to be saying really interesting stuff. I'm like, we go with monitoring well number 1, MW01. There's a reason for that. So, do we have probable cause? Step one for induced seismicity protocols published in the early 90s by Froelich. This is a figure from Jeff Bull, who worked for Chesapeake. Step one, are you disposing near or in basement? Yes, stop. Where's your formation? Directly above the basement. Well, we got probable cause that your injection zone could be a problem. Preponderance of the evidence. This is your background rate of seismicity 3+. We're doing this now. We got some good evidence things aren't normal. This is 3+. This isn't any earthquake you can measure. In my yard, I had a seismograph going, like most people do. Life was a little strange. I could watch about 100 seismic events a day come in. Felt about 6 of them. The dogs protocol, in case you want to know, we have 2 chairs up by the front window that the dog likes looking out of. If we had an earthquake, he'd jump off the one and go on to the other, because that's the way he'd be saved. If it was late at night, he would leave my mother-in-law's room and jump on me. I'm supposed to save him from the bed shaking. So, yeah, it got a little hairy when this was going on. And since we are the largest change in the history of the world, it's pretty hard to say, I think that's just a little anomaly. Another preponderance of evidence, the state acknowledged this. So Austin Holland was our state seismologist. He left. His assistant left. The professor at OU left. Nobody else is giving talks. Very likely, the majority of recent earthquakes, particularly those in central and north central Oklahoma, are triggered by the injection of produced water in disposal wells. April 2015. We noticed. Statistically, you noticed in 2009. You really noticed here. You're 2 orders of magnitude higher. We waited till here. Okay. Governor Fallon, we all know now there's direct correlation between the increase in earthquakes we've seen in Oklahoma and the disposal wells. I got put on a front page article on induced seismicity in the Tulsa World. Quote from Dr. Halihan, quote from the governor. We both said statements that were true, but as a professor, if you don't want a call from the dean, do not show up on the front page of a paper compared against the governor's quote. Don't do that. It's not good. Clear and convincing evidence. There's already a lot of publications out. So 2013, 2014, 2014, 2015, 2016, 2015, 2015. Okay, so the evidence is coming out as we're talking about it. A lot of times when you're talking about environmental issues, it's this has happened. Well, we haven't gotten the science done yet. This one, there was science being done already. So it was slow enough that there was stuff already coming out. The other clear and convincing, when they finally turned down the injection wells, we had less earthquakes. And I said, well, that'd be a really good piece of data, but before they turned it down, I was like, it'd be a really good piece of data that you turn it down, you'll see the earthquakes go down. Well, but we don't want to turn them down, it'll cost us money. If we turn them down and it doesn't slow down, then you were wrong and it cost us money. True. I don't think I'm wrong. Yeah, but do you have several $1 million to bet on that? No. But once you guys turned it down, we got less earthquakes. So pretty clear and convincing evidence scientifically that it was caused by high rate of injection right adjacent to the basement. Disposal wells. Several classes of disposal wells. We're dealing with class 2, spent brine from oil and gas field operations in oil fields. Class 2 disposal wells, people ask me, well, why do you guys do that? And we did that because of Kansas. It's all to blame on Kansas. A young Bob Dole, in terms of how old these problems might be, they're not that old, but they're pretty old. As a young kid, he was drinking oil field waste because they're dumping it in the streams. So kids were getting sick and things drinking that. And so they said, well, dumping it in the stream is a bad idea. We're producing in Kansas and Oklahoma concentrations above 100,000 parts per million typically. Up to halite saturation concentrations, 300,000-400,000 parts per million, and I don't know exactly what the halite saturation is, but it's pretty slushy. So what they decided to do, well, what we'll do is we'll go to deep disposal wells. And there was a good formation to do that with. But Kansas Geologic Survey has some really good information on that evolution of how are we going to deal with these fluids. We don't want to just dump them out at the surface. We'd like to have the oil and gas, but we want to do something with these fluids. So they came up with a Class 2 disposal well. Goal was to get the wastewater below the base of fresh water. We actually put it below the oil fields. So instead of just putting it someplace salty below the base of fresh water, we actually stick them below the oil fields. So it was a good spot to stick it. Regulations were built to ensure that we didn't get into the surface or along the well casing. We're going to do all these regulations to protect surface and groundwater, fresh groundwater, from any of these fluids interacting. So we had forms and regulations constructed, and people got mad at us about the forms during this problem because they said, these guys didn't tell us this. Like, because for fresh water it doesn't matter. Well, yeah, but it matters for seismicity, and the form was made before we got seismically active. So there was problems in the regulatory context that it didn't have information about things that affected a problem that didn't exist when they made the forms. I gave this talk and I used this picture. I used it from NPR because I wanted to make sure I didn't take a picture of a well such that I was implying that that well makes earthquakes, right? And I'm not implying this well makes earthquakes. I just wanted a picture of an injection well that exists in the world somewhere. And I gave this talk, and a woman from this company was the communication officer. She came up to me and said, you used a picture of our well. I'm thinking, yeah, it's from NPR. She's like, well, could you change the label on it? What do you want? Could you put that as properly engineered? Yeah, sure, I'm good. I'm good with that. That was her concern, is that she wanted me to point out that this is done properly. And that was a good point, to make sure that people didn't confuse it with, yeah, this is a way to make earthquakes. You put any of these up and they make earthquakes. Because they don't. Most of them are aseismic. And in terms of injection, we're producing oil up here, and this is the cross section running up and down through Oklahoma. We got the granitic basement sitting here. This is imaged as massive granite. The granite doesn't know that. If you look at seismic on that, there's really clear reflectors running through the granite. Several of them. We don't have any real boreholes to tell you what that means. But this is not a massive granite. This is a granite that has really distinct hydrogeologic structure with no data, or almost no data. So the disposal zone, the Arbuckle, there is the Reagan sandstone, which is a little skinny sandstone right at the bottom, but basically the Arbuckle's sitting on basement. There's about a 10-foot sandstone sitting on top of it, between the two, but functionally it's on basement. When you listen to most folks, they don't know the Reagan sandstone exists. They go, the Arbuckle in the basement. There's actually a little sandstone in there. And in terms of when the wells started having seismic problems, they said, well, are any of them connected to the granite? I don't know. Why don't you know? We never cared. We wanted to protect the top of the well. The engineering was to do the top of the well, not the bottom. So the drilling protocol was drill through the Arbuckle. When you start seeing pink stuff come up, stop. Well, that seems reasonable. Not if you're worried about the bottom now. So how many of you guys tagged granite? Oh, a lot. There was 555 wells we had to look through. And this is for 2016, but we demonstrated about half of them weren't in granite. The rest of them, we spent about $45 million plugging back. There's a big investment. I said if we did about the same investment, we could understand this problem scientifically. That number was too big. But on a distributed basis, about 200,000 each, we plugged back about 222 wells and took them out of the basement so that they would inject in the Arbuckle but not inject directly to the basement. For the Arbuckle, I don't know if the Arbuckle cares that much, but at least it helped buffer a little bit. So we think it had some help. I don't know if it helped. I don't know how much it helped. And then there's other things the wells were doing. So going through that process, when the seismicity started and they said, well, you guys should regulate the earthquakes, the companies legally couldn't say, yeah, we want you to tell us what to do about a problem that we didn't cause. Right? They had a weird legal situation of how do we discuss this. But they could say, we will do whatever you tell us to do. And the regulators said, well, we need the legislature to vote that we have the power to tell somebody to do something about something that the regulations don't talk about. They need to tell us that we can tell them about the bottom of their well. And the legislature said, don't ask us any questions about this. We don't want to take a vote on this to say we're voting against the industry or voting for the industry. So they said, okay, well, and there was a lot of discussion, and there's the legal version. My version is that, okay, well, we'll say something about the earthquakes, and if anybody squeaks, we'll have to deal with it. And everybody said, what do you want us to do? Okay, do this stuff. Okay, we're not squeaking. Okay, and we just started going forward with a context where it's okay to also talk about seismic activity, even though the regulations are largely talking about protecting freshwater resources. So getting over that hump was actually a fairly large hump on the science, or on the regulatory side. These things have tides like we talked about in the Arbuckle, but they're mostly confined systems. But we can watch those tides come in the wells. We can also watch injections kick on. And we started monitoring the system about when that 907 started. We don't have earlier monitoring data, but watching the data, you notice a couple things. You see the tides come through near the injection wells, and you see massive spikes. And when they inject, they don't inject, okay, we're going to inject at 100 barrels a day. They inject at, we're going to inject 100 barrels right now, and then we're going to wait, and then we'll inject again. And so you get these seismic hits, or not seismic hits, you get these sort of nuclear blasts of pressure increase and dropping down. It'll go up 75 feet, drop back down, and it just kicks it. And you're basically hydraulically hammering on it because you're injecting, not uniformly, you're injecting with pulses. And so you can see those effects in the wells. When they did lower the injection rate, they went basically from 2 billion barrels per year down to 1. And the monitoring wells went. Now, if you're injecting into a confined system where all the boundary conditions are constrained, and you slow down injection, but you're still injecting, pressure shouldn't go down in your model. Your model should be rising more slowly. Ours dropped immediately. So we'll talk about that in a bit. So you get these responses. You can think about it. We talked about that a little earlier. So that's that's Oklahoma stuff. We can think about other places. So South Africa noticed about this, and if you go to South African miners, they understand making their own earthquakes because they don't like dying. And if you're 4 miles underneath the rock and you make your own earthquake and it collapses your mine, you've got issues. Largely, it's the last mine project you're doing for a while. So they've noticed this for a long time, and they've been pretty good at mining without too much seismicity because they're trying to stay alive. Then we notice petroleum seismicity, surface reservoir seismicity, injection seismicity, natural gas production seismicity. And I point out that we've known we can make earthquakes for 100 years. And the reason I had to point this out was one of the things that was on the news is man is not capable of making an earthquake. It has to be natural because we could not possibly do this. Like watch the James Bond film. It's the villain goes and makes earthquakes. It's not that hard. But I had to point out we've known about this for 100 years, give it a context. And then something I didn't expect in it was they said, you're talking about examples in South Africa, and you talked about examples outside of the state. We only want you to use examples inside of Oklahoma. Yeah, I'm not doing that. So this is a Halihan figure from Caitlin Barnes. This is my Ph.D. student. I told her she could do anything about injection seismicity as long as she didn't study Oklahoma, because she wanted to study it. And so when we look at, you've got extraction and loading, so you can drain an aquifer, you can drain a mine, you can fill a reservoir, but we're talking about pretty tall reservoirs. These are the sort of 100-meter tall reservoirs. This isn't that 10-meter reservoir that you're dealing with. You're putting on a pretty good loading, or you're draining this thing out. One of the guys I was talking about how to make that it was purely natural was giving an example of a place where oil and gas production was occurring, and it was this little town in Mexico. And oddly, not only was I the guy who happened to be sitting in Stillwater, happened to be sitting in a seismically active area, happened to have background in physics and hydro, I also had a weird background in karst. And I recognized the name of the town. I said, isn't that where like the Cave of the Swords is? And I looked it up, and they've drained the water table by like 600 meters or something. And I'm like, it's mining seismicity. And so I pointed that out, and suddenly that example was gone. But the curmudgeon in my department said, you know, I love that. I said, why? He says, you know, that person was looking for any example they could find, and if that's the few that they found, and that's the one that they were trying to point to as a great example of not being induced by humans, you know that he's looked almost everywhere and that we've had a pretty exhaustive search. I'm like, oh, that's true. But in terms of those loading and extraction ones, people were trying to invoke that in Oklahoma, largely from rains and droughts. Except for we've had rains and droughts forever in Oklahoma, and suddenly it magically started and went up exponentially about the same time we were injecting a lot. So the other one is injection and then getting a pressure pulse to hit an optimally oriented fault. And I put optimally oriented on this because people kept trying to make any fault have an earthquake. And it's not any well and it's not any earthquake. You got to have the right setup. And so there's this nice paper from 1939 to talk about this, and this is train coming into a station. And the train didn't touch the water table, but the water table went up. And then the train left the station. It didn't pump the well, but it did drop it down. And you're changing the weight, and you're indirectly affecting water fluid pressures at a distance. And so that's one mechanism, and people were trying to invoke that. And you're pointing out that, well, that's 2/100 of a feet. You can do this, and people worry about this. If you're filling a surface water reservoir, you can make big, giant earthquakes. People think it's a little hard to prove, but they think there's some association between some fairly large seismic events and filling reservoirs too fast. And they also think draining out groundwater, there's places you can look at where they've done that and they've induced seismicity. So this is a mechanism, but they were trying to invoke it in Oklahoma without having enough mass movement to do that. And you could calculate that relatively precisely. And sorry guys, there's not enough water moving around here to do this. So there's the other mechanism. And I could have drawn a nice force diagram, and I could have shown you a nice stress field on a fault and all these sorts of things and looked at fluid pressure and given you a few variables, which if I was talking to a group of scientists, I might do that. But I showed you a guy in Australia that was moving a giant rock sphere because he's got a 1.5 horsepower pool pump running. Much easier for the public to understand how a little bit of water pressure can move big rocks. And yeah, it's not a nice scientific diagram, but they pretty quickly understood if you squirt underneath the granite, you might be able to move it. So I got calls from the Netherlands. They wanted to come over. I got to be interviewed by the Germans, the Dutch. I spoke in German. I don't know what I said. The Koreans came over. The Japanese came over. The French came over. The Dutch at least had earthquakes. I asked these other guys, I said, what are you guys worried about? They said, our investments. I'm like, oh, okay. Their money was in Oklahoma. But out in Holland, what was interesting is people consider Holland more left than Oklahoma, right? So Oklahoma's sort of a more right context. Holland's more of a left context. Went down the same way. People felt like the folks in the rural areas were being abused. They felt like the energy industry was out to get them. This was one company. This is basically one consortium runs this setup. And so they can adjust a lot easier as a decision than Oklahoma, where we had hundreds of companies operating in terms of operating injection, in terms of operating production, in terms of operating equipment, in terms of being in a regulatory context across different things. We had to move hundreds of parts, but it came out the same way that you guys are picking on the rural people and the industry's out to kill us all. So it didn't matter what the politics was, it came across the same way. So the early work on this came out of Rocky Mountain Arsenal, and it was detected by a monk. Regis University out in Denver, the monk had a seismograph to teach with, and he was detecting earthquakes. And I got somebody from Regis University let me know that their monk was the first person. So I don't think he published it, but he was noticing. Now, their biggest quake was after injection ceased. There's the well, there's the earthquakes. The pattern doesn't just circle around the well. There's the well, there's the earthquakes. It doesn't just circle around where you inject. The pattern isn't, hey, I injected at this depth and I made earthquakes where I injected. But in Oklahoma, they were saying, well, the wells only go to this depth and there's no earthquakes around it, so it can't be that injection well. Well, interestingly, the physics has never shown us that pattern. So in terms of that, I had to show these folks that here's the pattern. It's nowhere near the injection well, and then if you look here, it's closer looking. but it's shooting all along this fault and you're getting these earthquakes. It's not something centered around where you're injecting. And it continued for about 15 years post-injection. So you don't just turn it off either. They came up with statements about that. Injection rate was about 4 million gallons per month. They were injecting the contaminated wastewater. I had to point out, folks wanted me to tell them that's not oil waste. That's true, it's not. You're injecting fluids with other people's waste in it. But I had to say this wasn't an oil field related thing. And they said, no, it's not us. Well, we think we see earthquakes related to you. It's not us. So they turned it off. They said, trust us, it's not us. They turned it on. They said, trust us, it is you. And they shut that down. Now, the interesting thing about this spot is you go, well, yeah, they were injecting straight into the basement. True, but they actually did work. And they said, okay, well, what's our pressure here? Well, we're under pressured down here. Oh, well, then you're fine. You got plenty of room. You just got to go up to hydrostatic pressure and don't fracture this thing or something. Turns out an underpressured reservoir, if you change the pressure fast enough, that change in pressure is what is important, not the fact that the whole reservoir can take fluid. So you got to look at what's the rate that you do. And there's people that debate about rate versus volume, but I'm a rate person. I'm into the what size pressure pulse are you kicking out? Because even in this underpressured reservoir, you're making plenty of earthquakes. Now, when you had that, this is the 70s. If you haven't seen The Rise and Fall of the Great Lakes by the Canadian Film Board, highly encourage it. It's on YouTube. But there's also one that's not on YouTube that I'd like to get a copy of. If you got a copy, let me know. It's The City That Waits to Die. And it's a Canadian Film Board film about San Francisco and sitting there and waiting to die. And they were going to fix that because they know they have a big fault running right through Sacramento or right through San Francisco, and they're going to fix it. What we're going to do is we're going to develop an experiment in earthquake control. We're going to test it in Colorado, and then we're going to go out to San Francisco, drill injection wells along the fault, and turn them on. And we'll fix San Francisco's problem. Mid-70s, we had some really good drugs. At the time, we thought by about now we'd have full control over earthquakes. We had a full understanding of how to manage them, how to run them, and we'd be running injection wells to control seismicity. So this is the actual titles, an experiment in earthquake control. And what they had was they had an oil field that they said, yeah, you guys had some Rocky Mountain Arsenal problems. Yeah, we think we're seeing some problems. What should we do? Well, we could study it. Oh, that's a good idea. It's no longer a protocol that you have a problem and you want to study it and you put money and you figure it out. But back in the day, we did that. So the USGS came in, got some famous names involved, and what they did was they made their own earthquakes. So turn on the injection wells, get the seismicity going. Some of them occurred around the wells. Some of them occurred at a distance. And they took nice pictures of the earthquake machine, and they were basically had the valves, and they're making their own earthquakes at about 2.3 million gallons per month. Try to write that proposal now. I'd like to generate earthquakes in this area, da-da-da-da. Why? Well, because I'd like to move San Francisco. Yeah, okay. But it happened. So if we look at their experiment, there's the earthquakes within 1 kilometer of the bottom of the wells. The orange ones are the ones that are at a distance. Normally it's at a distance. And then they're monitoring their pressure, and if they kick over their critical stress level, boom, they make earthquakes. Okay, so they were playing with it and going, can we make them? And they were injecting and pumping back. They could turn them on and turn them off within a day because they had control over the fluid pressure. So they're like, yeah, we could build this. We haven't built it, but we've demonstrated you could play with it. The problem is controlling it. So if you're going to do that in San Francisco, I do that the day after it falls down after the next date. Then you might have some ability before a bunch of stress builds up. I wouldn't do it right now. But in theory, you could think about this, but I would do it after a big earthquake and it's relieved all the stress before you start trying things. And maybe not start with San Francisco. We have done a long-term earthquake machine. In Paradox Valley, Colorado, they had bad water. And they said, well, we could have better water with some earthquakes. I said, well, how many are you going to make? We don't think we'll make too many. Will we notice? You'll notice some. What's the alternative? Oh, bad water. We'll take it. And so they took the deal. They wanted to go with better water. And in general, they controlled it, but there's a few times they had to pull back. And they're like, whoa, that was bigger than we thought. And so running one of these earthquakes machines ended up having it's a bumpy ride. It's not particularly controllable, but they tried in this situation, and they've had to pull back on the stick a few times. So there are examples where people have tried for other reasons to do this, and they've demonstrated it's not super easy to run one. The other one is thinking about the Kaiser effect, and this is thinking, a lot of it's theoretical, but it's thinking about the seismicity, and that as you inject over time, you should watch the seismicity move away from the well. And so we've been watching for these effects, which in Oklahoma, if you're standing in Oklahoma, you're within 15 miles of an injection well. Pretty much anywhere I drop you in the state. So if you're looking at moving out over time and you're saying, which injection well was it? Over time, that becomes harder to tell. And we're all injecting at the same time with different things. So it says this problem could get worse if you try to look later in terms of figuring out what's going on. I was really thankful when Art McGar posted this, because I went to a seismic conference early on, and we were talking about seismicity in Oklahoma, and I had a basic question. I said, so you seismic folks, you guys study this stuff, and we've got some longer faults, and we don't know much about our faults for some of them. I said, what's the biggest we can make? You know, like, is it down at 5 or 6, or can we make a 7 or 8? And I was waiting for the really distinguished person in the room that knew all these things to stand up and go, don't have to worry about anything bigger than this. And they're all looking at each other like, it could be pretty big. Well, you're freaking me out, and I was hoping one of you guys give me a better answer. But Art McGar came out and said, I think it's about a 6, which was handy because it was good to tell the public that I wasn't looking at 7 and 8s as something I couldn't discount, at least in the published literature. There's still some issues at that rate, but I had published literature to go, looks like you can inject up to about a 6. And the top value's Oklahoma, so we've done several right up in this range. Yay us. Now, in Oklahoma, what does that mean for us if we get up there? Here's California having 150 people call in to Digifeel it, or go on the web, to say, hey, I had a 5.8 earthquake here, we felt it. Okay? And this is 10-kilometer scale. Macaulay-wise, yep, we're shaking, yep, we noticed. Here's Oklahoma, here's a 5.8. 60,000 people told them, and this is hundreds of miles, this is a 100-mile scale. We woke up people in Houston and Chicago. Our attenuation isn't the same, but the number is. And so folks in California are like, yeah, but you guys just get 3 or 4. Do you notice those? Oh yeah, we noticed 3 or 4. Well, it doesn't cause any damage. Oh no, it causes damage. But we have different attenuations, so the number itself was problematic to communicate because we didn't have the same number in terms of how much shaking is going on, and nobody knew Macaulay scale. So thinking about shaking and talking about it this way didn't translate to anybody. They knew, well, you had a 5.8. That's probably something you felt. Yeah, we also have 4s every day. Well, you don't feel those, though. No, we feel those. We can actually feel down to close to a 2. We can notice. The dog gets upset at 2s. So it wiggles the chair a little bit. He jumps to the other chair. So we did some work on the well side, and what we looked at was, you know, there's places where you have induced seismicity where they only have like 1 well. And so we were wondering whether, with distance, how much distance do they go? And, you know, if it's a pressure change, it should show up about like a well solution. So we looked at a team solution. And you get these different solutions if you plot the team equation and you're looking at hydraulic head and distance. Well, that's harder to look at. So what we did was we did the percentile change and looked at it that way. And when you do that, all those curves collapse and you're just looking at a function of distance. You dropped it into geometry. And so when we did that, we did this for about 9 different locations, and they fit exponential decays really nicely. The pattern is still kind of screwy, and the distance for about 90% of the earthquakes is about 20 kilometers. which we were regulating for 10. So it's about twice as what you would think, and the pattern is not a nice circle or anything, but it does a nice job of saying, yeah, well, it's basically a hydraulic system. And so the controls on hydraulic systems and pressures should be allowable to change that system and adjust it. And you could think about how much pressure you're generating and control that. And instead of injecting with pulses, maybe get something to smooth that out and think about the hydraulics of it. Been very hard to get folks to think about the hydraulics of induced seismicity. They think about the fact that they're shaking and seismologists are telling you about the earthquakes. They don't think about what's making them. But injection-induced seismicity is a mechanism tested beyond a reasonable doubt. When you can turn them on and off same day, you're beyond a reasonable doubt certainty that you can make an earthquake with this. It's more common than generally recognized, and if you get to a critical rate, and there's this debate about rate and volume, but Froelich thinks it's rate. I'm into what's the total pressure. Weingartner said it was rate in Oklahoma, and Walsh and Zobak said it was the volume. I think it's what's the pressure pulse you're getting moving out from your well and how high pressure you're getting in terms of its change from background. And can be triggered by fluid overpressures less than 0.1 megapascal, about 15 psi, half a tire. If you're at the right optimally oriented fault, you don't need a lot. And so if you can start going 15 psi, you're asking me to not change it very much, yeah? Not if it's the right fault that wants to move. You don't need a lot, is what the research says. So these were the things we knew, and it said some things we needed to do about that. So going to hazard mapping, if we're going to map that out, how do we do that? And so we had workshops about that. What should the maps look like? How do we do it? Which ones do we put in the induced bin? Which ones do we put in the natural bin? How do we decide which one is which? Do we assign different mechanisms for the induced ones? Is that a quarry that let off some dynamite? Is that caused by hydraulic fracturing shallow versus injection at depth? How to separate, how to properly treat the data. I think we're still working on that, but there's now reports out. So this was the seismic hazard map that you have no real hazard. There's New Madrid as an actual hazard, and this was, you don't have any real hazard and there's nothing really in northern Oklahoma. This is what if you want to build a building and you look up your risk and what you have to do for building a building, this is what the database looks up. And still today in Oklahoma, that's what the database looks up and says you've got no seismic risk in northern Oklahoma. In terms of attenuation, we were in this range. These words were tricky because the press kept wanting to say disastrous or catastrophic. And I said, no, those mean something to us. We're very strong or ruinous. Man, why do we call it ruinous? Because it's super hard to get the press to use the word ruinous. But our worst is ruinous, not catastrophic, not disastrous, and not very disastrous. So we thought, okay, you'll be about in this range. And we've had chimneys collapse, poorly constructed buildings seriously damaged. There's one I didn't expect is that, hey, that building fell down. Well, it wasn't built very well. That's true. Well, that chimney, if it was built better, it wouldn't have fallen down. Were they planning on a 5.8? Well, they should have. Why? So there was these debates about, well, that shows us which buildings aren't built well. It's one way to look at it. And that's not a debate I expected. And we've had sort of this range of problems. And it's with induced work, it's been very, very localized. So if you ask the carpenters in Stillwater, which neighborhoods have problems? Oh, that one has a lot of houses. They're all screwed up. What about that neighborhood? Nope. And if you ask on campus, and if I had a campus worth of people here, and I said, how many of you guys have felt induced seismicity? The ones that raised their hand are all working in the same buildings. Because my building shook, some other buildings shook, other buildings didn't shake. All on one campus. And so the data is very, very weird. We had an earthquake that hit me in the butt one time. I went up to this guy who was doing all the seismic monitoring. I said, was that right below us? He said, oh yeah. Great. So the pattern is tricky to communicate. The names we use is tricky to communicate. The numbers changing. We're roughly roughly 1 unit different from California. Okay, so our 4s are their 5s, roughly. Splitting this apart and coming up with these divisions of the data and whatnot, it was tricky. And so defining these zones, it's not a clean thing because the seismic folks don't know the hydraulic folks. The hydraulic folks have trouble communicating with the seismic folks. And so even on a science basis, it's tough to define these little zones. This was a fun one. McNamara looked at, we happen to have, if you didn't know it, we have a key little problem in Oklahoma, or little location in Oklahoma. It's called the Cushing Oil Storage Facility. Cushing is, if you drive into Cushing, Oklahoma, it's the pipeline crossroads of America. So if you look at a terrorist map, you go work for Homeland Security, there's a big bullseye on Cushing because if you take it out when all the heating oil is going to the East Coast, you freeze out the East Coast. So they pointed out you didn't need a terrorist. We have a fault running right through the Cushing Oil Storage Facility that is oriented about the same way as one that had a 5.6 on it in a Prague quake. We suggested about this one could occur at that fault directly beneath that facility. Nobody really liked that paper. And it pointed that out. We did have a high 5 right about here, and it did knock down a significant number of things in downtown Cushing. So we've run an experiment on that fault that says you can cause some damage. Those folks build their tanks according to the way Californians build their tanks. They think about seismicity in the construction. So they're reasonably confident, but they haven't run the experiment yet to see how confident they should have been. This made people nervous and made, when there's extra earthquakes around Cushing, very quickly everything is shut down. So the hazard here, potential of exceeding this, and this is Macaulay magnitude 10 plus. It's in that disastrous, let's go crazy range. Have some implication for infrastructure design standards. Yeah. Don't shake your large oil storage facility with all your pipelines crossing with something that large. I had to spend a lot of time convincing, and this, I didn't think I needed to convince a lot, but I had to convince a lot a school to run an earthquake drill. Now, if you go to shakeout.org and you go, I don't know anything about how to run an earthquake drill, they give you the slides, they give you the handouts, they give you everything. They give you the day to run it. They tell you the times to run it so you can run it with everybody else in the country. They walk you through every last step. And I said, well, can you guys do this? They said, well, we don't want to scare the kids. I'm like, oh, well, I have a kid in Oklahoma school and I'm talking to the guy from my kid's school. Don't you guys do 3 active shooter drills a year? Yep, we want to protect the kids. I can tell you right now, the 3 active shooter drills freak them out. Telling them to climb under their desk and hold on, I don't think that's that bad. But it was a big discussion about whether it would freak the kids out. So we finally got them to do one, and several schools never did. But teaching them to drop, get under the desk, and hold on was a big thing. They didn't want to do that. So I would put that up and try to get people to convince schools to do it. But it was something that was a lot more pushback on climb under the desk and hold on, do that for 30 seconds one day in October. Can't do that. Okay. I gave them options. By the time I used this slide, I was getting tired of giving them the options. One is the environmentalists wanted to ban injection. And well, do you want to figure out who's actually causing the problem? No, just shut down the oil industry in Oklahoma. Okay, so that's an option. It's not necessarily good or bad, but it's an option, but it's got a lot of side effects. For the seismic active zones, and that's already the method that the state was using for some, is they would just turn off wells. The ostrich method was, we're not causing any problems, and I listed it as the previously used method. These are things that I suggested that nobody has really done for the most part. One is to set a maximum rate and say you can go up to a particular rate, and we've done that a little bit relative to other studies in nearby wells. We've done that a little bit now. This is the one I thought would be helpful. And that's the maximum water cut. That if you had a dry hole and there's no oil, you still have water in there, but you don't have any oil. So you lost. You drilled a hole and you didn't make any money because there wasn't any oil in it. I was suggesting that a wet hole was also that you lost. You found oil, but you had too much water. We had wells that were pumping 60 plus gallons or 60 plus barrels of water per barrel of oil. You lost. Drill something that produces oil. All you're doing is producing salt water, and you happen to get a slight level of contamination in there that you're going to make money on. So, but that was something that in the data set, you're like, turn that one off, turn that one off. The total volume will go way down because you guys are the ones producing all the water. But it was something they weren't ready to do, is to pick on individual wells unless they were directly tied to seismicity around it. Funding alternative methods, they looked into quite a bit. Very cost sensitive, about 50 cents a barrel to do injection. And if you think about that and you've got 10 barrels of water per barrel of oil, you've got about a $5 disposal cost. At $50 oil, it's not a big thing to notice. If you go up to $5 solutions, and there's a lot of $5 water cleaning solutions per barrel, and now you got 10 barrels, you got $50 in disposal cost, you've got no money. So fairly price sensitive depending on how much water's coming out. And we had fairly wet fields, so it would basically make them uneconomical if you wanted to switch to a $4 to $10 solution. Up in the Marcellus, I'm told they use up to upwards of $18, $20 solutions. They don't have much water to deal with. So you can go, okay, well, relative to how much we're producing, that's not a big hit. We could do something like that. But for us, you couldn't get much over $1 to maybe $2 and still be profitable. So you could say, well, then you're not profitable, shut it down. And that's that too much water cut solution issue. Alternative location, this is one that they've selected. I'm worried about this one. They've started injecting into old oil fields into shallow places. There's a risk to the shallow groundwater of getting nice, hot, salty stuff squirting out. We have a lot of stumped wells in Oklahoma. And that's that, okay, well, we cut off the casing, we put down a stump, and then we cover it up over. Stump wells are really good places to connect to places that you're now pressurizing for disposal. So injecting below has earthquake problems. Injecting shallow ends up being the old Bob Dole problem of impacting at the surface. So, but it's something that we're applying. We can model the reservoir flow with field data. It'd be great to know, where does the water go? What water? The billion barrels per year that you put down there? It went away. Yeah. Yeah, where? And I made a statement to me. I said, is it good to rely on magic as your method for disposal? And I got laughed at, but I'm like, that's essentially what we're relying on. And they go, well, you know, it costs a lot of money to drill down there. Yep. But you're injecting 1 billion barrels a year. You might want to know where that goes. That way, if that shuts off for some reason because the mechanism doesn't work anymore, that you're ready for it. And what well interactions exist. So can you come up with well protocols for injection that you can limit seismicity? The injection rate, the injection pattern, how close they can be, doing the science. And then legal and regulatory uncertainty. Getting the companies to be able to exchange data in a legal context that they're not all nervous. And maybe that's a neutral party. They do this in Oklahoma for energy. And so if you're going to go in an area and they all need a lot of energy, they don't want to tell you what they're drilling and they don't want to tell you what they're drilling, but they'll tell a neutral party, yeah, I need to drill during this time period. Yeah, like 5 guys around you are drilling during that time period. Can you guys slide back by 30 days? Yeah, we could do that. And they basically have the neutral party go slide forward, slide back, and they fit in the energy needs. It'd be similar to saying, how much are you guys disposing? Can you guys slow down? Can you guys speed up? Can you guys adjust? And doing that sort of thing. We don't do that yet right now. And so we've got the earthquake machine sorted out with, we have class 2 injection wells. We have earthquakes. They're going down, and so that's nice. But this stuff in the middle in the machine, we don't have that characterized. And that would cost, I would say, on the order of $50 million. You're going to need to drill a couple holes. A couple holes would be $10 million. But at least have some data about what are those reflectors in the basement. They're really good on seismic. What are those actually? How much fluid do they take? Are those hydraulically conductive zones? And you know, where are some of these faults? Most of our faults are strike slip. They don't show up on seismic. They show up when they move. There's one, it just moved. Okay, good. So thinking about some of those things would be great, but we would need to do an investment. And 50 million seems like about the right price to me, but I always say numbers that seem reasonable because you would need to spend that much to actually collect some data. But people go, well, we'll just collect data on earthquakes at the top and we'll figure it out. Yeah, I'm not sure you will, but there's a lot of work going on collecting earthquakes at the top and a lot of people looking at the bottom of Oklahoma, and there's new stuff coming out all the time. But there's a good call for drilling a couple holes. At GSA, this is the other student that's going to talk. This is a map that came out in the mid-90s by one of our professors at OSU called Jim Puckett. And this is the potentiometric surface of the Arbuckle. It's got this hole in the middle. And so he's gone back and gotten scout tickets out and tried to reconstruct what did this thing originally look like. We keep coming up with a hole. So if you notice, it's basically a drawdown cone, but it's a couple counties in scale. Now realize we're injecting 2 billion barrels a year, we turn it down to 1, and you drop pressure. One of the only ways to do that I can think of is to have about a billion barrels per year water loss in your confined system. And one of the only places we can take it is south. I don't know of any place geologically I could take it except for south. But I think this thing leaks, which is probably really good for disposal, but it'd be good to know where it leaks to. He's looked at building what's the original potentiometric surface there, because everybody that's tried to model this, the pressure goes up. No flow conditions around the side, confined system, it pressures up. This thing in reality doesn't pressure up. But we don't know why. There's hypotheses, but it'd be good to actually know. So there's a website for this, and they actually have all the stuff on there. So if you want to know about Oklahoma seismicity, if you're missing something on that website, they'll post it up there, which is really good. And then lists of references. They're wonderful. So, questions about earthquakes?
The preceding program was brought to you as a community service lecture by the Edwards Aquifer Authority. For more information, visit edwardsaquifer.org.